Okay, in this second lecture I'm going to be talking about some of the implications of losing physical complexity in rivers. The first lecture I emphasized the sources of physical complexity and why it was important. So now we can talk about what happens if you lose physical complexity. And the basic objectives for this section I think would be to understand how human activities have altered the type and the magnitude of river physical complexity, understand the implications of some of that loss of complexity for river form and the processes that create function in rivers, and then explore a case study from the headwaters in the Colorado Rocky Mountains. So first of all, how do our activities alter river form and function? There are two basic levels at which we influence rivers. The first one is what I'm calling indirect effects. So we're not doing anything right in the channel or the river network itself, but we're still altering the rivers. And that's mainly through changing the land cover. And land cover usually refers to the vegetation communities. So if you have timber harvest, for example, or you're changing the native vegetation into crops, or altering the native vegetation through grazing, if you're urbanizing the catchment of the river or some portion of the catchment, all of these can change the land cover. The other basic form of an indirect effect is through changing climate, which of course we have been doing for a period of time now, but we've become much more aware of it recently. So if you change the precipitation and temperature of a given river's catchment or drainage basin, then that in turn filters through all of the components of the basin. So it changes the vegetation, the rate at which bedrock weathers into sediment and soils, the stability of the hill slopes. So precipitation and temperature is sort of the first stage, but then it filters down through all of these other levels that influence water and sediment coming into a river. And really, whether it's changes in land cover or changes in climate, the effects on river are that you change the materials going into the river, and that's primarily water and sediment, but also nutrients that are used by plants and animals, and contaminants that can influence biological communities. The other basic way that we alter river form and function is by directly changing them, so doing things in the channels or valley bottoms themselves. Big one is altering the flow of water and sediment through the rivers. So dams are one of the primary sources of that around the world, but we also take water from points in a channel and move it to other channels or other drainage networks through diversions, for example. Another big effect is to alter the form of the channel. So channelization, usually you're making a multi-thread, like a braided or anabranching channel, into a single channel, or you're making a meandering sinuous channel straighter. Dredging, usually you're trying to increase the cross-sectional area of the channel so that floods, for example, don't go overbank, or there's a minimum depth of water that's maintained throughout the year for navigation. Bank stabilization, you're trying to prevent the banks from eroding. But one way or another, we're altering the form of the channel. I emphasized connectivity in the first lecture between the river ecosystem and the greater environment through the 6 degrees of connection. So we can also alter connectivity if we build levees, or if we build these transportation corridors, which would be things like roads or railroads next to the river. That typically dramatically limits the connectivity between the channel and the adjacent valley bottom and floodplain. Dams, of course, limit the connectivity of water and sediment moving downstream, and of organisms such as fish moving upstream. So the net effect of all of these activities is usually that we tend to reduce physical complexity. If you think about a sinuous channel that's been dredged and has stabilized banks, it's much more uniform and simplified. And although there are human activities that increase connectivity, most of the things we do decrease connectivity. So you end up with these fairly simplified, disconnected river corridors. So what are the implications? What does it matter if we change complexity, and particularly if we lose complexity in rivers? It gets back to the things that I was emphasizing in the first lecture that complexity creates. If you lose complexity, you tend to lose the abundance and diversity of habitat on which plants and animals depend. So you have fewer organisms, you're decreasing the abundance, and you also typically lose biodiversity, whether it's a reduction in the number of species present in the channel and floodplain, or a reduction in the diversity of those individuals within a species. I used the example of cottonwoods in the first lecture. If you have cottonwoods that primarily germinate immediately after a flood, if you put a dam in and you reduce the number of floods or the size of the floods, you're probably going to reduce the opportunities for cottonwoods to germinate as new individuals, so you end up with just an older forest. You also often lose resilience. One of the things that allows an ecosystem to recover following a big disturbance, such as a flood, is that there are places where organisms can get out of the way of the flood. So there's secondary channels or parts of the floodplain where fish, for example, can take refuge during a very high flow and swift velocity. If you lose complexity and you go to something that's more like a simple uniform conduit, then you lose those shelter spots, and it's harder for organisms to recolonize an area, river, after a flood, for example. So you lose some of the resilience to disturbance. If you're losing all these other things like abundance, biodiversity, and resilience, you're also losing the ecosystem services that I talked about in the first lecture. Things like clean drinking water, navigation, flood control, fisheries. And I also emphasized retention or storage in that first lecture. So again, if you lose physical complexity, you lose retention. Things like water, sediment, nutrients, contaminants just stay in transport. They don't get stored along the river corridor. The nutrients in particular, there's less opportunity for stream organisms to take them up. So that is one of the reasons that you lose biodiversity of species and individuals. Okay, so a specific example of this from the headwater rivers in the Colorado Rockies, and specifically Rocky Mountain National Park. Old-growth forest tends to produce a large number of trees per area of ground, so a dense forest, and big trees. They have a very large diameter. If you combine old-growth forest and a wide valley bottom, as you can see in this photo, there's a lot of downed wood on the floodplain here, and this was taken before the mountain pine beetle started to affect these headwater riparian forests. There's a channel at the far rear right in this photo, and there's some secondary channels that you really can't see in the middle. So there's lots of wood as a result of that old-growth forest. It's accumulating across that wide valley bottom and floodplain. It's creating log jams that are big enough to span the entire width of the channel. So they're very effective at creating those backwater effects and storing sediment and nutrients, as I talked about in the first lecture. So then you end up with these obstructions in the channel that force flow across the floodplain, so you get overbank floods. Some of that water infiltrates into the floodplain, so you have a high water table, and that supports some of the wetland species that wouldn't be present otherwise. Those floods across the valley bottom are typically shallower and slower moving than the floodwaters in the main channel, so some of the sediment and nutrients that are being transported drop out of suspension and are stored on the floodplain. You get the secondary channels that I talked about in the first lecture that branch and rejoin, and there's different habitat in those, and again, more abundance and diversity of habitat. So you end up with a very high diversity of plants and animals, both in the channel and floodplain in this scenario. And just an illustration of that, this is looking upstream in the main channel. You can see the stepped appearance. There's log jams that are storing a lot of sediment and creating a plunge pool at the base, and they're very closely spaced. And what you can't see in this photo is that there are smaller secondary channels that branch away from the main channel and then rejoin it across other portions of the floodplain. Similar type of scenario happens if beavers are present. Beavers, of course, build dams, and because of that, ecologists call them both ecosystem engineers and keystone species. Ecosystem engineer refers to any plant or animal that alters the surrounding environment enough to create habitat for other species. So in the case of beavers, they build the dams, and the dams are just like the log jams that I was talking about a moment ago. They create an obstruction in the channel and a backwater, and that forces water across the floodplain. Some of that water infiltrates, so you end up with this very high water table, and that creates habitat for wetland plants. Willows, sedges, and rushes, for example, really like those high water table areas. So the beaver is engineering an ecosystem for those plants. Beaver are also an example of what ecologists call keystone species. If you think of an arch, the keystone is the central portion of the arch, and if you remove that keystone, the whole arch collapses. Well, if beavers are creating all this habitat for other species, if the beavers are removed and their dams fall into disrepair, then much of the habitat that they create vanishes, so the other species that were dependent on that habitat leave the area as well. So, analogous to that example that I just gave with old-growth forests and wide valley bottom, if you have beaver building dams in an area of wide valley bottom, as you see in that lower photo, it's the same process that I talked about for log jams. You have more overbank floods, some of that water infiltrates, you have a high water table, you're storing sediment and nutrients across the valley, you have smaller secondary channels, you have a lot of abundance and diversity of habitat for both plants and animals in the channel and the valley bottom, and you have more biotic diversity. This environment, as I mentioned in the first lecture, is often referred to as Beaver Meadows, and there are lots of studies by ecologists that show that there's a really heterogeneous habitat. There's a couple of photos here illustrating that. You can see in the photo on the left that there's areas of ponded water, there's water flowing over the dam on the photo on the right. There are portions of old beaver dams that are now vegetated, so they're slightly drier and they're supporting different vegetation and animals that are in the ponded water areas. So there's a lot of heterogeneity and complexity. Again, ecologists have found much greater diversity of species, that's sometimes known as richness of species, with pretty much everything they've looked at in Beaver Meadows, from bacteria and microbes up through insects, plants, mammals, fish, waterfowl. There are a lot of organisms that use these wet meadows. They may not live there year-round. They may be species that live primarily in the upland, but they come down and use this wet valley bottoms periodically. And certainly the sediment that is forced onto the floodplain and stored in floodplain environments as a result of the beaver dams has a lot of organic material in it. So there are nutrients such as carbon, nitrogen, and phosphorus in particular that are dissolved in the water, and they're also in particulate form in the sediments. And again, they're being retained in these environments. They're not moving downstream nearly as quickly as they would if you had just a very simple, uniform channel. So, getting back to this idea of the implications of loss of complexity, if beavers disappear from an area for whatever reason, then eventually their dams fall into disrepair and the ponds begin to drain. And there's a couple of photos here also from Rocky Mountain National Park showing different stages in that process. If you don't have the ponded water and the overbank flow, then eventually the water table in the valley bottom declines and it becomes a drier environment. Once it's a drier environment, you start to get animals such as voles, these small burrowing mammals, that eat something called ectomycorrhizal fungi. These are fungi that are present in drier soil. The voles eat the fungi, but they also disperse the fungal spores in their feces. And this type of fungi is critical for the survival of certain types of conifers, such as spruce and fir. And if the valley bottom is flooded, the voles aren't going to go in there, they can't burrow, and the ectomycorrhizal fungi can't survive. But as the valley bottom dries out, the voles disperse these fungal spores so the fungi becomes more common in the soil. That facilitates the colonization of the valley bottom by conifers, as you can see in the photo on the right here. Behind that pond that's shrinking and drying with time, there's some spruce and fir coming into the valley. So basically you go more towards an upland, dry environment as the water table declines and the vegetation changes. And sometimes these are referred to as drier grasslands or woodlands rather than the wet beaver meadows. So prior to very intensive human manipulation of forests and rivers, both in this environment in Rocky Mountain National Park and worldwide, old-growth forest was much more widespread, and beavers were much more common across both Eurasia and North America. There are two species of beavers, Castor canadensis in North America and Castor fiber in Europe. And historically, beaver were present from Siberia over to Spain and down to southern Europe and up into the Arctic regions. If you had those sources of complexity, such as old-growth forests and beavers, their dams and log jams were more common, the beaver dams and log jams. So this headwater multi-thread channels that were closely connected to the adjacent floodplain were also more common. So these river corridors and valley bottoms really had a lot more physical complexity and much greater ability to retain water, sediments, and nutrients. Another way to look at this, if you take away beaver and old-growth forest, of course the basic configuration of the valley doesn't change. You still have a floodplain present. What changes is how that floodplain is connected to the channel and the retention that's associated with that floodplain. So on the left here, there's a very simple drawing, a plan view or map view, what you'd see if you were looking at a map. The blue squiggly lines are channels that are branching and rejoining, main channel and secondary channels. Each of the green blobs is supposed to be a willow. On the right is a side view of that main channel, and the brown lines are a beaver dam in there, and then the secondary channel's off to the side. And when the beaver dams are present and they're forcing overbank flow, you've got water, sediment, nutrients spreading out across the floodplain, being stored there, and the water infiltrating. If the beavers disappear, and that's happened for a variety of reasons, from direct trapping to other causes, again, the valley geometry doesn't change. What changes is that the beaver dams fall into disrepair, you lose the overbank flood. So you go to a scenario more like this, where each of those little symbols of 3 lines are supposed to be grass clumps, and the triangles are conifers. So as the beaver dam falls into disrepair, flood flows are more likely to be contained in that single main channel, and they're going to move downstream more rapidly. The velocity is going to be higher, they're going to be more erosive, so that single main channel becomes larger and deeper with time. It can cut down or in size, and the adjacent floodplain dries out. As you don't have the overbank floods, the water table drops, some of the carbon and nitrogen stored in that soil is oxidized or lost to the atmosphere, and you're not getting the increment of additional storage each year during overbank floods. To put this in a little bit more quantitative terms, I'll give you a very specific example. This is based on work that we did in the headwater rivers of the Rocky Mountains, and we looked at how much carbon was actually stored in the floodplain. So the y-axis here is megagrams of carbon per unit area of floodplain. And the brown bars are carbon stored in wood, dead trees basically, for old growth forests, those trees that have fallen over and take a long time to decay on the floodplain. The green bars are the living vegetation, and the white bars that are on below the x-axis, the 0 point, are carbon stored in sediment, so organic matter in the floodplain soils. And these first 4 bars are all valley segments that were very wide, low gradient, and had either old growth forest or beaver dams. And if you look at the size, the vertical extent of those bars, there's a lot more carbon stored in those types of valley segments than where you have either a more confined valley segment or younger forest or no beaver dams. So another way to express this, those broad, low gradient valley segments constitute less than a quarter of the total river length. If you look at how extensive they are up and downstream and the river network as a whole, they're not very common. But when we extrapolated from our measurement sites based on that proportion of the river network that those types of valley segments occupy, they constitute less than a quarter of the total river length, but they actually store 3/4 of the carbon stored in the valley bottom. So these wide, low gradient sections are disproportionately important in storing carbon. And again, I'm using carbon just as an example here. You could, I think, have a similar story if you looked at sediment or nitrogen or some of the other nutrients. The point is that if you have physical complexity and you have this high level of connection between the channel and the adjacent floodplain, these spatially limited segments are very important in creating retention and ultimately resilience in these river networks. So, what's happened historically? What has changed complexity in these rivers? Well, worldwide, there's been a dramatic loss of old growth forest. In the world as a whole, humans have reduced forest cover by about half of what it was prior to the development of agriculture. And globally, we've mostly eliminated old growth forests. And old growth forests are important because they produce those really large diameter trees and abundant wood that can form the big log jams and create this complexity and retention. If we look at beaver, ecologists estimate something like 6 to 12 million beaver in North America at present, but historically, there's a big span in the estimates, but there were a lot more. At a minimum, about 4 times as much, and maybe even more, so 50 to 125 million animals. And this is hard for us to imagine now, but beaver would have been present in every environment that had forest, from the riparian forest in a place like Arizona or northern Mexico, up to the fringes of the Arctic in Alaska and northern Canada. If we look just at Rocky Mountain National Park, one of the things that I've done there is map the distribution of abandoned beaver dams, and there were a lot more beavers there in the past than are at present today. An example is this place that's specifically called Upper Beaver Meadows. That's the proper place name for it. Doesn't have any beaver today, but we used ground penetrating radar, which is shown in this photo, to image the depth and the type of sediments that have been deposited in this segmented valley since the glaciers melted 15,000 years ago. What we found is anywhere from a third to a half of the sediment deposited since the glaciers retreated was associated with beaver dams and beaver ponds. So there's this long-term effect where the beavers have been responsible for a lot of retention and complexity and productivity in these river systems, and it's changed dramatically very recently. So what does it matter? Well, this is where the title for these lectures, both of these lectures, comes from. I now refer to these rivers that have lost physical complexity and retention as leaky rivers, because they leak water, sediment, nutrients, everything downstream. That material is transported at a much greater rate than it would have been when they had the physical complexity. So if we look at this globally, look at rivers in the context of the global carbon cycle. Carbon is coming from terrestrial environments, from forests, grasslands, and comes into the freshwater network of rivers and lakes and eventually goes out to the oceans. But what comes in from the terrestrial environment is a much larger amount than what gets out to the oceans. So something is happening in the freshwater network. And this is a very schematic illustration of that. The numbers on here are petagrams of carbon per year. They're average global fluxes. Petagram is a very large unit, but it's the relative numbers that are important for our purposes. So we have 2.7 units of carbon coming off of the land globally. It goes into rivers, lakes, wetlands, the freshwater network. About 1.2 of that is returned to the atmosphere. That's through respiration of living organisms, plants and animals, releasing carbon to the atmosphere. Another 0.6 goes into what's called the geosphere, which is storage in sediments. And this could be storage for a few hundred years in a small headwater floodplain, or it could be storage for 10,000 years in the floodplain of the Amazon or a big river delta. The remaining 0.9 units goes out to the ocean. So if you look at this very simple diagram for a moment and think about the implications, the details of how carbon is partitioned, whether it goes into the atmosphere, the geosphere, or out to the ocean, depends a lot on the complexity and the retention and the processes that are going on in global river networks. And one of the things that biogeochemists and ecologists and geologists are starting to realize is that as we lose physical complexity in rivers, you're more likely to get a lot of the carbon and other nutrients coming into rivers going straight out to the ocean, which can create its own problems. Things like eutrophication, or an excess of nutrients in nearshore environments, can create what are called anoxic zones, where there's a lack of oxygen, and you have they're also known as dead zones, places where fish and many organisms can't survive, for example. And if you remember the first lecture, 70 to 80% of the total length of most river networks is headwater rivers. So the whole carbon partitioning between the atmosphere, geosphere, and ocean really starts with the headwaters, where that carbon is coming off the terrestrial environment and entering the river network. So these are the references that I've been citing in each of these slides as we go along, but I think what I'd like to leave you with is this idea that, first of all, rivers are not just simple physical conduits for water and sediment. They function as fairly complex ecosystems, and the physical complexity is very closely tied to the biological complexity as expressed in things like biodiversity. And if you lose physical complexity, for whatever reason, there are some very important implications in terms of how the river functions as an ecosystem. So, for example, in terms of how many organisms and what variety of organisms it supports, so abundance and biodiversity, and also how material moves through the river network, whether that material is water or sediment or carbon. And I think it's important that we understand these implications, because if we view the increased transport of materials such as carbon as negative, then we have to think about ways to enhance or alter physical complexity or restore it in rivers and limit some of that downstream transport of carbon. Thank you.